should speak in English because she's speaking in English, and so she'll speak about protocol mappings and digital learning for sparse protocol support vector machines. My subject.
Hello everyone. As Professor said, my name is Somayeh. I'm Study Center of Supervision of Sao Paulo, and I would like to start with the concept of classification. In fact, the classification problem is to learn a function that to predict the true class of a new observation. Support vector machine is one of the most well-known tools in machine learning for classification. One of the challenging tasks in classification is to deal with the specific type of data sets that its feature set is in a higher dimensional space, and the number of samples is a few. In this situation, we have some challenges. For example, machine learning models become susceptible to overfitting, which is known as a bias, and also the requirements for both memory storage and also computational resources increase. So dealing with these challenges is an important task in classification. One of the most attractive methods to tackle these challenges is the dimensionality reduction that can be broadly classified into two primary components: feature extraction and feature selection. The feature extraction methods identify the most compact and informative set of features. In fact, generates a new set of features. So the original physical meaning associated with the features may be lost. But the feature selection methods preserve the original input space and choose a subset of features according to the optimal criteria. Importance of dimensionality reduction in classification. SVMs have been extended to the feature selection by introducing sparsity using norm constraints and the coefficient vector. The most straightforward methods to attain a sparse classifier is to integrate the zero norm into the regularization. That results in a non-convex problem with non-polynomial time complexity. So it is typically implemented by approximating zero norm with for example, the conventional approach for approximating zero norm is to replace zero norm with norm one. That results in a non-smooth optimization problem. Another approach is approximating the zero norm by using the concave optimization-based approach. Now we have a quick review on in the literature. Support vector machine, the first method we can consider. We consider a binary classification to classify endpoints in the n-dimensional real space. The training set T is the set of all vectors xi and yi, such that for all I from 1 to m, xi belongs to Rn, and yi belongs to the set of +1 and -1, representing as positive class and negative class, and yi shows the class that xi belongs to. The main idea of SVM is to find a hyperplane that divides the space into two disjoint regions such that all data points in the positive class lie in the positive half space and all data points in negative class lie in negative half space. The primary goal of SVM is to find a hyperplane such that the distance between this hyperplane and the closest point in each classes are maximized. This distance is called the margin. Here there is a figure for showing an outline for SVM. The blue points shows the
Can I do like this is better?
Yeah, much better, much better.
Let's just too bright.
in this figure, the blue points are the samples in positive class and the red points are the samples in negative class. The red line is the desired hyperplane in SVM that is called the decision boundary. For maximizing the distance between this hyperplane and the closest point in each classes, SVM classifies all data points with margin at least 1. So as we see in this figure, we have two lines parallel to the red line. These lines are called supporting hyperplanes, and all vectors lie in these hyperplanes are called supporting vectors. Due to the parallelism between these hyperplanes, the distance between them can be determined by the fraction 2 divided by the Euclidean norm of W. The larger margin has some benefits. For example, a larger margin makes a classifier to be less sensitive to the small variations in the training data, and also reduces the risk of overfitting, so it allows to a better separation between two classes. The goal of SVM is achieved by solving the optimization problem 1. The objective function, this problem maximizes the margin between the hyperplanes, and the constraints guarantee that all data points are classified with margin at least 1. This problem is called hard margin SVM. In fact, hard margin SVM finds a hyperplane that maximally separates two classes and no data allowed in the margin or on the opposite side. So hard margin problem is susceptible to the presence of outliers, and also it is difficult to adhere the assumption of linear separability in the real world data sets. So the soft margin SVM was proposed in order to handle the non-linearly separable data sets, also to be less sensitive to the presence of outliers. The soft margin version is in model 2. Model 2 represents two competing measures. The first term is the margin maximization as we see hard margin, and the second term is the error minimization to analyze the wrongly classified samples. The figure in this slide compares hard margin SVM and soft margin. As we see in the soft margin version, the soft margin version allows the data to the presence in the margin or on the wrong side. SVM classifies all data points by assigning them to one of two half spaces, of two disjoint half spaces. Fun and Malbasarian in 2001 presented proximal support vector machine in which the samples are classified by assigning them to the closest of two parallel hyperplanes that are pushed as far as possible. They presented model to be the first term of this function of this model maximizes the margin between the hyperplanes with respect to both W and B to consider both the orientation and the position of hyperplane. And the second term is obtained by replacing norm 1 in soft margin by norm 2 for obtaining the smooth optimization problem. The main idea of PSVM is to replace the inequality constraint with equalities. In fact, this modification changes the nature of the optimization problem. In PSVM, the hyperplanes on both sides of the decision boundary are not boundary hyperplanes, but they can be considered as the proximal hyperplanes around which the samples in both classes are clustered and they are pushed as far apart as possible. Here there is a figure for comparison between SVM and PSVM. In 2006, Mangasarian and Y presented generalized eigenvalue PSVM by eliminating the requirements of parallelism between the hyperplanes. In fact, GEPSVM or JEPSVM identified two proximal hyperplanes P1 and P2 such that each hyperplane is closest to one class and as far as possible from the other class. The figure in this slide shows that in JEPSVM the hyperplanes are not necessarily parallel. By considering matrices A and B, as I introduced here, they presented the optimization problem for to determine the hyperplane P1 that is closest to the positive class and as far as possible from the negative class. I introduced the matrices in this formulation here, but they proved that the optimal values for W1 and P1 is achieved at an eigenvector corresponding to the smallest eigenvalue of the generalized eigenvalue problem form. By an entirely similar argument, we can formulate a generalized eigenvalue problem to find the hyperplane P2 that is closest to the negative class and as far as possible from the positive class. After determining P1 and P2, a new point X is assigned to class K based on its proximity to the nearest hyperplane. In 2015, Popo et al. Presented another formulation for JEP-SVM via the least squares approach. And they established that the least squares optimization problem is equivalent to the generalized eigenvalue problem in JEP-SVM. By considering G and H as I introduced in the previous slide, and consider the Cholesky decomposition of G and H, in which U1 and U2 are the upper triangular matrices, they formulated the least squares optimization problem with N1 regularization as model 6 to integrate the feature selection into the classifier construction. And after that, they presented the block coordinate descent method to solve this optimization problem. This method has two main steps. In the first step, beta in model 6 is fixed, and the optimization problem 7 is solved to find the optimal value for alpha. And in the second step, the determined alpha is used in model 6, and model 8 is formulated to obtain the optimal value for beta. Model 6 is a non-smooth optimization problem. So solving it is computationally expensive. Adhering to this issue, Lee et al. In 2021 presented the least squares optimization problem with norm 0 in the regularization and presented model 9. This model is non-convex and with non-polynomial time complexity. To treat with 0 norm, they introduce a function as the number 3. This is a continuous non-convex function, and by regarding this function, they reformulated optimization problem 9 to optimization problem 11. And then they applied the block coordinate descent method, as I said in the previous method, and also DCA, difference convex algorithm, to solve this optimization problem. The approach of Lee et al. Has a couple of limitations. The first, they introduced a new non-convex function, but it is not clear that what are the advantages of this function compared to the commonly used functions in the literature of feature selection. And also, their method and similar methods do not directly with 0 norm, and they can apply only an approximation for 0 norm. To address this issue, we consider the least squares optimization problem with L0 regularization, and I focused in this problem and apply two methods that directly deal with 0 norm.
This is the same as problem 10, right?
12 is the same as problem 10.
Same, yeah.
12 and 10 are
12 and 10 are the same problem, right?
Yes.
Yes.
Yes. We consider the optimization problem and apply another method to treat 0 norm enhancement. First of all, the block coordinate descent method is used to solve problem 12. In the first step, beta is fixed in this problem, and alpha is determined by optimization problem 13. It is easy to solve this problem. The second step is fixes alpha and computes beta by solving this optimization problem 14. From now on, I focus on this optimization problem and apply two methods that directly deal with 0 norm in this optimization problem. The first method is based on the work of Beck and Halak in 2018. This method is a two-stage method. The first stage starts at an arbitrary point and finds a sparse vector by applying the binary search method. So the input of this algorithm is the arbitrary point beta, the target value rho, and the feasible set B. The output will be the sparse vector beta prox. Given that the binary search method works on the sorted arrays, so the first step finds a sorting permutation sigma. To recognize whether a vector is a sparse vector or not, we should find the value of the function that is noted here with dB sigma, this function. We should obtain the value of this function to recognize that whether a vector is a sparse vector or not. So the second step finds the value of this function at the beginning of the range 0 to n and compares this value with the target value rho. If the function value is less than or equal to rho, then algorithm terminates and returns beta as a sparse vector. Otherwise, in the third step, the value of this function is determined at the end of the range 0 to n. And if the value of this function is greater than rho, then algorithm terminates and returns beta as a sparse vector. Otherwise, step 4 sets k low equal to 0 and k up equal to n, and binary search begins. If the difference between k low and k up is equal to 1, then algorithm terminates and the sparse vector has been found. Otherwise, the middle point of the range k low to k up is determined, and in the next step, the value of the function dB sigma at k min is determined and is compared with the target value rho. If the function value is greater than rho, the binary search continues in the upper half of the range. And otherwise, binary search method continues in the lower half of the range. And the algorithm continues until the binary search is finished and returns a sparse vector. The second stage leads the sparse vector to an optimal solution for our problem. So the input is beta prox, scalar lambda, and feasible set B, and the function f. The first step finds a vector beta 0 that minimizes the function f such that the non-zero elements of this vector is a subset of the non-zero element of the sparse vector. After that, to recognize whether a vector is an optimal solution for our problem or not, we should compare the value of objective function at vector beta with the value of objective function at 3 specific vectors. Steps 2 and 3 determines those three vectors. These vectors are obtained by small changing, small changes in the non-zero elements of vector beta. After determining those three vectors, step 4 compares the value of objective function at vector beta with the value of objective function at those three points. If the inequality in step 4 is satisfied, then algorithm terminates and beta is an optimal solution for our problem. Otherwise, step 5 determines a vector among those three vectors that minimizes the objective function and returns this vector as beta calculus 1. And algorithm goes to the step 2 and continues until convergence to the optimal solution for our problem. The next method is based on the work of Goto et al. In 2017. Before explaining the method, I provide a definition and a theorem. In the definition introduces the largest k-norm of a vector beta. And that is defined as the summation of the k largest absolute values of this vector. Theorem explains that for any integers k, norm 0 of beta is equal to k if and only if k is the smallest one, such that the difference between norm 1 and largest k norm is equal to 0. According to this theorem, we can reformulate our problem by replacing norm 0 with the difference of norm 1 and largest k norm in the objective function for all k between 1 to n plus 1. The optimization problem 15 is a standard DC program because the objective function can be rewritten as the difference of two convex functions, and so we can use the DC algorithm for solving this optimization problem. At the first, according to the theorem, we need to find the smallest k such that the difference between this norm is equal to 0. Given that the difference between norm 1 and largest k norm is non-increasing in k, so the binary search method can be applied for determining the smallest k. So, if ECA is applied for our problem 15 with some k and finds an optimal solution such that the difference between norms is equal to 0, then we can conclude that the true value for 0 norm is at most k. So we need to integrate binary search method into DCA to solve our problem. Here I provide the steps of DC algorithm for solving our problem. The DC algorithm has two main steps. The first step finds the subgradient of the second term in the DC representation. So the first one, step 1, select subgradient for function gamma. And in the next step, we need to solve a convex subproblem as we see in optimization problem 16. These steps until the stop condition is established and find the optimal value for beta and optimal solution for our problem. We move to the next section for reporting experimental results. We applied our method, we implemented our methods on 13 data sets. Table 1 shows the samples and features for each data set. Column 2 is the number of samples, and column 3 is the number of features for each data set. In this experiment, we conduct the results by applying tenfold cross-validation to validate the classification accuracy. And the optimal hyperparameters are estimated by applying the grid search method and also the performance of each classifier is reported in terms of classification accuracy. Table 2 reports the accuracy and the number of selected features for each data set and for each classifier. The second column shows the results for classical SVM. The third column shows the results for L0 PSVM, method of Lee et al. And the last two columns show the results of our method. Method 1 is the method, a specialized method of Beck and Calvert, and method 2 is the specialized method of Goto. As we see in this table, method 2 demonstrates superior classification accuracy compared to the other methods in 9 data sets, across 9 data sets. And for example, for some data sets, for example, ionosphere, spam-based, and vehicle theory, method 2 shows significantly higher classification accuracy than the other methods. For some data sets, for example, for wine and for heart, the method 2 shows a slightly lower accuracy than method 1, but it outperforms L0 PSVM and CSVM. Regarding the sparsity, our method, method 1 and method 2, are sparser than CSVM and L0 PSVM. In each cell, I forgot to mention that in each cell, we have 2 values. The first value is for classification accuracy, and the second value is the number of selected features. Our methods are sparser than L0 PSVM and CSVM, and with comparison between our methods, we conclude that method 2 is sparser than method 1 for some data sets, for example, for gum, for coffee, and for example, for ionosphere, WDBC, and for some data sets, method 1 is sparser than method 2. But both of them are sparser than L0 PSVM and CSVM. So this study considered the feature selection method to extend PSVM to the feature selection by inducing sparsity using zero norm. The obtained results show that our methods are sparser than CSVM and L0 PSVM. The comparison on our methods shows that the specialized version of Goto et al. Exhibits significantly higher classification accuracy than the method of Beck and Kellogg across some data sets. We can imagine three directions for future research. We can develop our methods to the imbalanced data, in which the available data for one class is very small compared to the data of other class, and we can extend the method for multi-class classification problem, and we can develop the robust version of our methods in the case of data uncertainty. Thank you so much for your attention. If there is any question.
Thank you, Somayeh. And you are now open for questions.
Please. Okay, I have several questions. Thank you so much for your presentation. This is a very nice idea. Do you know, I think I'll go from the last slides to the beginning. So, how is CPU time on each method here? Like, it's kind of the same, you didn't report, right?
I did not report the computation
But you know
time.
more or less what's going on.
And there are no significantly difference between our computational time and the computation.
Nice.
We focus on the sparsity of our method than computational time.
Did you try on larger data set like CIFAR or any something like that? This might be something that people will ask for, more features and samples.
No, the reason is that this is the data set using the previous paper from
Liaison.
Okay.
So we could compare it then, because it's not implemented there.
I see.
We just implemented our variation using their table for the first two columns.
Okay. And the other two columns you did. Right. My more theoretical question, can you go back to the other two, I guess?
This is the Malak or the Goto et al.
Method one, this one, How do you solve the step one, the initial step? Like, how do you solve this optimization with this subset that's your saying? Is it simple or
You fix some variables in zero.
Oh, okay.
The support is given, so you can only.
That's simpler problem then.
Yeah. Now I understand. I think I didn't understand correctly
The inclusion is.
The inclusion.
But the inclusion is hard to.
Yeah, that's what I mean.
This inclusion is key.
I see. Okay. And for the next one, my last question, I promise. You have to find a subgradient, right? You can go one more. And this is easy to find in this case, right?
The DCA, because the next slide.
The next slide.
Next slide. In the next slide.
Yeah,
Yes,
this is it's kind of easy, right? Because you're just doing, you can consider this a norm one function on the less space, I guess. And
I didn't basically use that, so. How
do you compute the subgradient of gamma?
It's easy for computing this, but I didn't put the formulation here.
It's a closed formula, right? It's a closed formula?
Yes.
It is, right? Yes. It's just a curiosity because of this.
Yes, but I think it's less.
Yeah, right? Yeah. Okay, thank you so much.
More questions? Let me see if there's some questions in the chat, but sometimes we need to check. Just a second. Okay. Here. Share. Share. Here. No questions in the chat. So, nobody, no more questions? If it's not the case.
Okay, just a question.
Okay, thank you, Mario.
This is stopping criterion that you put at the end, the difference between two consecutive objective function values is small. Is it quite reliable, or you can convert to something that is also? I mean, you stop when the two consecutive function values are consecutive function values are multiplied, don't you? Okay.
Excuse me, I'm not sure I got
The stopping criterion. The last line.
this.
Yes, the stopping criterion for the algorithm.
It's just function values, right?
This is the stop condition for our algorithm.
Yes, for DCA, this is.
Yes.
He's asking if it's reliable or if you can stop too soon. Is it easy to find the
Yes, we
maximum?
can prove that the time for this algorithm is polynomial and very soon it will be age.
Polynomial.
Or no,
High rate of conversion, something like that. I mean.
I would, how can I say? What I know this algorithm is terminated very soon in our data sets. And also,
One question would be, if you change epsilon, does it, how does it change a lot? What are the outputs? For example, if you try to go to a
Yeah,
higher
small
precision,
epsilon. Yeah, do you have any?
do you see that the output is still changing? Or how did you select epsilon?
I select epsilon by research method.
But it is it's a hyperparameter.
Oh,
It's using the grid search.
research. Because probably this is what Mario means. If you make smaller, probably the number of the k here, which is the number of non-zeros, will change, right? Somehow. I guess so. Yeah. If you are more loose here on this problem 16, you will have a more less sparse solution.
But that's why the grid search is a good idea, because at the end of the day, the grid search is using as criteria to choose the hyperparameters.
Hyperparameter.
What is the one that you are using? What search?
Grid search, grid. Busca em grade. Busca em grade dos hiperparâmetros. So she just there like epsilon is 10 to the minus 1, 10 to the minus 3, 10 to the minus 5, minus 7. And then at the end of the day, she tries many and selects the one that gives the best generalization. So this is dealt in some sense by the grid search, which is very expensive.
Yeah.
Whatever, we don't care.
Some people are like looking for algorithms for instead of using a grid for the hyperparameters, try to use some optimization on that.
Yeah.
Using an LLM or something
I'm
like
talking
that.
about that with Mario.
This would be very nice. Yeah.
Helps aqui.
Okay.
Instead of using grid search, using intersection across groups.
Yes, something like that. Yeah, this is nice. Great.
Thank you so much.
Thank you.
So, Thank you, people, and see you next Monday.
Next one, yeah.
Felipe, aí.
Oi?
Isso é Felipe, tá aí.
Felipe.
Não é o.
Felipe, você tá aí?
Ah, não sei.
Não, Felipe não tá aí. Tchau, tchau, pessoal.
Tchau.
Obrigado.
É semana que vem, assim? Ah,